So, and basically is that we are going to talk about RISC-V, and then the journey again, along the so far 15 years. How bad is it? How tough is it? And then what is the prospect of it? And then we're going to show you what we've done so far. So, my name is Yuning. You can Google me, or you can Google RISC-V laptop, the world first RISC-V laptop, or you can Google the most expensive RISC-V laptop. So you should be able to find me. Right? You should be able to find me. And then we call our company called DeepComputing. So we are either make it, see whether we can make something deep. So I don't know why, you know, we made this company, we named it DeepComputing, and then suddenly this year, you know, DeepSeek. I don't know why they call it DeepSeek. So everything from that onward is asking me, and coincidentally, my surname is exactly the same as DeepSeek's founders, and also from the same province as well. So people asking, are we related? So, but anyway, so DeepComputing we only do RISC-V products for consumer electronics. So, and you will see that we make 2 generations tablet, and one 4-core, one 4-core, one 8-core. And then we have we've done one smart speaker and using the 4-core. And so far, the SoC is not good enough for us to make another smart speakers. So, and the most important thing we do is so-called modern personal computing devices, which is a laptop or AI PC, so far people call it. So, and this is the first Roma, and it's sold for $5,000. So we only make a few hundreds. So, and for people keeping it and remembers it, and we put it into a few computer museums, especially in UK, in one of the national computer museums. So it's the first RISC-V laptops. So, and RISC-V is pretty boring. So, and lose basically doesn't make money. So I make something fun. So I invested the company in making RC car, the best RC car in the world, the most expensive as well in that category. So around average selling price is around $100. And also I make drones as well, so the balloon drones. And we sold this balloon drones in, I think it's in 2004's RISC-V Summit in North America, when the government starts shutting down Chinese drones. So that's part of it. So RISC-V, anyone knows RISC-V? I hope everyone here knows RISC-V. And I, as a evangelist or advocate, and we always say RISC-V is big enough. The analogy to RISC-V is Linux. 40 years ago or 50 years ago, I think it's 40 years ago, no one knows how big Linux is, right? But now, how big Linux is? It's monetary, right? No one can believe that, right? So, and I would say that regarding the openness, especially now, the world is so divided, you know, with geopolitics, right? And openness is one of the things that we as a human, and to counter all these divide. And same as technology, so open source and open is very important. So and hopefully RISC-V can occupy 1/3 of the ISV market. So that's pretty big, you know. x86 ARM and then RISC-V. So if you now start working on RISC-V, and later on why I say that is a big market and big opportunities, because you can see so far all the big names working on RISC-V, but they are not fully invested in yet. So there's a lot of opportunity, and you guys work on it and become famous on it. You know, you think a lot. Raylan is one of those guys, same as me, putting Android onto RISC-V. You know, a lot of hassles, a lot of difficulties, But the journey along is amazing, right? No one can believe a few guys can put Android, right? But that's the thing, you know. And as me, you know, as a DeepComputing, making laptop consumer electronics, we can do a motherboard later on for a laptop in 4 months and 5 months mass productions. It's faster than anyone in the world. ASUS, Acer, HP, Dell, you know. That's the way we can see. So RISC-V journey is actually I assuming you guys know RISC-V, and this year is 15 years. 15 years. So it's not short. So and earlier this year we ratified the most important standard or milestone called RVA 23. Means that we have a standard set of instructions we can work on. And when we look back, x86 actually has gone through a hard time as well. So before they become monopoly, or now they dying, you know. So that's just like a human, you know. You grow. I think x86 is from end of 70, 80, 90, and 2000, and then reached to the peak as 2010. You can see 50 years. So we reached to the top before they forced it up. And ARM as well. I used to run Lockheed feature phone. Probably you guys too old for you guys to touch it. Most of you guys are still in university or what, and never touched Lockheed phone before. Lockheed used to monopoly the whole mobile phone market. So at that time, each mobile phone has around 9 to 15 ARM IP inside. So ARM actually gone through from 80, 90, 2010, and 30 years for them to reach to 64-bit OS, and it's taken a very considerable amount of time as well. So, and RISC-V actually 15 years, I'm quite amazed. So, and it took us around took us about 15 years to reach having an SoC with 2 gigahertz, and then 12 nanometer, and then support 64 DDR. Actually, it's pretty amazing. So took ARM 30 years to do it, and took a similar time for x86, and for RISC-V it's just 15 years. This is considerably half of their time. But the problem is that, and you can see x86 is they got their hands on affordable PC, and then affordable server for the internet age, and then ARM go on to mobile, from feature phone to smartphone, right? So and RISC-V, people often ask what RISC-V for? AI, right? We all talk about AI now, and this lunchtime we discussed, right, why NVIDIA has such evaluations, right? Because AI is just even bigger than the internet. So you will foresee a good example. You can imagine 10 years later, probably university, 80% of the lecturer will be gone. Will be taught by the robot, and they have much more knowledge than the teacher you have now. They have much more deeper knowledge than any one of the professor, right? Because this human just can't cope with the knowledge you can remember, right? We forgot things, but large language model, they don't. The more people put in there, the better they are. The more better answer they are, the better brain they are. So you can see AI it's going to change every single industry, especially around knowledge. So RISC-V has to go around the AI. So, and I would say that, looking at the history, x86 is from US and driven by US. And I would say it's fully closed. They don't license ISA to anyone. is owned by the x86 ISA consortium, which is primarily is Intel AMD. And ARM, it licensed IP to everyone want to make a chip. If you guys want to make a chip yourself, and you can go and license from ARM. And they may charge you a lot of money, they might not charge you. But the ARM successful is part of the effort globally, especially for all the SoC firm. You can see when we can count how many SoC and that ARM makes ARM. Infineon, Europe, STMicro, Europe, and NXP, Europe, and then in the US side, and there's a lot more Broadcom available, blah, blah, blah. And then on the Taiwan is the MediaTek, in China, Ovina, Realtek, and a lot. It's driven by the global, the successful, right? And we call it, and the most important thing is the TSMC, right? If everyone used to be, and like Intel, they make everything themselves, even the fab. So that we'll see the ARM trigger the change of the manufacturing as well. So that's the TSMC support, so it's global. And RISC-V, original from US, so from David Patterson, we used to meet a very, every time I make a new product, I give it to him and let him feel RISC-V getting into people's hand. So from US, from Berkely, and then that's why Sci-Fi is formed, right? Sci-Fi is still having a hard time in the 10 years, trying to prove the model is going to work. And they migrate to Europe. The whole foundation migrate to Europe because, and anything you mix it in US, belong to US. Even open source. So they migrate to Europe, in Switzerland, neutral company, neutral land. And you will find that because of geopolitics, most of the SoC now is made by China. So I will see that Sci-Fi is the biggest customers all in China, right, or Asia. And I would say that the whole ISA, the ecosystem, belongs to everyone who knows it. If you know RISC-V, and now there's a lot of open source CPU IP, you can put it to FPGA, you can make your own chips. So that you will never be able to do back in ARM or x86. It's very good for academic. It's exactly the same as Linux. Exactly the same as Linux. Before, in the Unix time, you try to make an OS is mission impossible. But now, with Linux, you can make, anyone can make an OS themselves, if you know how to make it, right? So that's it. That's how do we make a RISC-V successful reality? I think we're getting there. I have a free milestone for our company. For example, 1 year we're selling 1,000, 1 year we're selling 10,000, and then once we hit 100,000, that means that the company is getting there, getting successful, and so has the RISC-V. So we can see the problem of a new technology is deadlock. We have no hardware. Before I make laptop, no one makes body hardware. No one believe how bad is the software is, right? No one believe that. So, and the hardware guys are waiting for the software. The software side are working on QMIL, but the QMIL is so far away from actual hardware product you can sell. So, and this is the deadlock side. Hardware guy waiting for the OS guy, application guy waiting for the OS guy, and then just keep spinning around. You know, it's so classic. And all we had to do is that I decided to make a laptop. It's the same as the reason why Linux put it on the desktop. So, and same reason for it is we had to put it into a mass market to good for the ecosystem. RISC-V is made into MCU, microcontroller, a lot, embedded assembly of small system. There's a lot of those MCU, but those didn't help didn't help any the RISC-V software ecosystem because it's so close. It's very simple. And we try to make it into the laptop market because laptop is the most sophisticated consumer electronic. Once we know how to make laptop, we make tablet very fast. Usually, for example, for the last 2 tablets, once you make laptop, we can mass produce it within 3 months. So laptop is the most complicated one. So, and once you get it done, then you can make it mass produce. And that's the reason why we make laptops. And the other thing is that once we make a laptop, so and a lot of guys making the SoC IP. For example, right? I said to the IP Crest the other day, say, why your single core performance so bad? When software is bad, you need a very high single core performance CPU. Right? And to compensate the bad of the non-optimized software. Right? So, and that's why you can see I feedback a lot of problem, and also SoC. Most of the SoC guys, they try to make the SoC, we saying that they don't know what they make from their target market. They make the SoC very complicated. So we feedback to them, your SoC is very complicated. So we along with making the product, we telling all the supply chain what is supposed to be, what can be done better, and same when we make the laptop and we finding out we need a very big commercial developer system. That's what Ubuntu is. So we tell them we need to support RISC-V, and then we have a story around that. So I talked to them first thing for the commercial channel. And Ubuntu is so classic, you have to give me $1 million and wait for me 9 months. So that is a classic business. But you know, because RISC-V, we managed to inspire people and motivate people and to make things forward. And because it's selfishly, it's basically I tell, for example, last year I said to Canonical CEO said, you know, Mok, you know, do you remember how painful losing money when you're making your dreams? He said, I know. You know, do you know what year Ubuntu start making money? Right? So he knows the painful story. He says that let's get RISC-V done. So that's why we have a very good support from Canonical with Ubuntu support, with all the green light, with all the things they never be able to do it for x86 and ARM. So that is why you inspire people for openness, especially those who are doing open source. That's why we come here. We try to get people, the software guy in open source, to understand open hardware. So, but actually, oh, what happened to this? What did I do? I didn't do nothing. So let's move back here. So, but it's very hard. But it's very hard when we piloting all the challenges. That SoC guy, I give you an example. When Sci-Fi designed the IP, I used the first IP U74. So at that time, I said, I never let you to make it into a laptop. So people have different agendas. And then when the SoC guy said, when I make 4 core, I don't know what is it for. Right? I don't even know what customer is. So people have different agenda and different timeline. And before REA 23, even worse. Right? Sci-Fi U74, I don't know what REA 20, right? And then you have P50, REA 22, and then all the software guys just go bananas. So which one I should support? Right? So Canonical say, I'm making OS. Which way to go? So that is the problem with recommendations, right? So, and because the other thing is that if you look at the whole RISC-V ecosystem, how many guys in Sci-Fi? You know, a few hundreds. Compared to ARM, a few thousands. So how many guys in SoC guys, Starfire, a few hundred, compared to MTK, 10,000s. So people not having same as me, right? I'm just a laptop company. Compare myself to Asia or ASU, man, it's incomparable, right? So because all other resources, when we're making the product, is stress, very stress, right? So, and that is the challenging of paralleling. And same as Canonical, you know, they're already very generous. But we had to tackle one by one. So, first thing, now this is example when I close the loop, after make the motherboard, we tell everybody, so that's what you're supposed to do. Whether you listen or not, it's your problem. So if you don't listen, I will not be your last customer. Right? So that is the different stage you involve different partners. So by the time I make two, just now, later I want to show you, I make 2 generations of laptop myself, I fed up with it. So then I start making motherboard for framework laptop. So they're going to talk about framework later on with a RISC-V motherboard for framework laptop. And also, once we make the hardware ready, so now we can spin Ubuntu to full support of RISC-V. And sooner or later, when the upstreaming effort is done, and Ubuntu can publish their image especially for RISC-V. So that is the way we tackle problems. Yeah, that is the journey, you know, along my time with the, you know, I managed to save $1 million and save 9 months' time. So with partner with Ubuntu. Yeah, that is the laptop I used to make. You know, it's not framework. It's very painful. You know, I make needy every 6 months or 9 months. I make a motherboard. So I make this motherboard. I can put it back to here because the customer use this doesn't know how to replace. There's no way they can replace the motherboard here. It's dead, body dead. Just come in. Just come in. Just come in. Sit down. Right? Even take your pictures. Just come on, feel free, come in. Don't be shy. You are the futures. Not us, we're too old, right?
Yeah, they are the futures.
Yep, they are the futures. Students are always the futures. Yeah. So, and yeah, we moved on AI. I'm very, very lucky that we are in the AI age before I retired. So, and now the AI wants DeepSeek open source. The effect of DeepSeek is very important. They on top of Llama and then open source, they distill their own model. They save a lot of training resource. They make it better. They open source it, and then because they open source it, they can distill all other models as well. So you can see the models. The only way this world is just not human. The brain is getting better and better and better and better in the open source as well. Everybody can prove it's better. That is the important things. So sooner or later, you might be able to run your brain on your laptop very efficiently, or the laptop with better batteries and less compute powers. So we have inference with training. Soon, you know, just like post train. Yeah, you can do multicast. If you go down to frameworks booth, you can see the rack, right? Daniel's here. You can see the rack can run the 671B across 4 or 5 frameworks mini desktop. It's going to be better and better. You will see it's shrinking and shrinking. So one day you can run everything on your laptop. You can ask them just even better than any of the professors. It's scary. So, and as I say, you know, once we get onto, we lock out our direction of RISC-V AI, we will be all the way onto AI. Now we need to solve is our market is always open source developer with open source hardware. And then one of the open source requirement for like Ubuntu official support, we call it upstreaming. So upstreaming is one of the horrendous bureaucratic process in open source, right? So, and that's why I find it out this is the most horrendous. I ask people opinion, so I ask Linus and Grass. What people supposed to come on in, don't hide. When you see me, you have to come in. Right? So, don't be shy. So, and that's the beauty of RISC-V. You know, I'm just nobody. You know, I'm nobody, but I can talk to anyone. Come on in, sit down, feel free. Come on in. So we have plenty of time. What we're saying that it's not crowded enough, so probably we are quite good. It's pretty crowded here, right? It's amazing. There's not, actually hardware, software people do care about hardware. Right? It's just no, we are not advertise it good enough. So that's the beauty of RISC-V. You work on RISC-V, you find a problem, you can find the world's best people, famous people help you to solve it. So I spoke to Greg, and Greg will be our ambassador of upstreaming of all our product and most of the SoC we use. And then we can manage to convince, as I said, Ubuntu as well, and then Fedora and Red Hat coming. So it might not be fully accurate, but you know, here we go. You can see that is whoever work on RISC-V, don't be shy. You know, don't be shy. You are going to work with the best people in the world, and which is very open, right? You're a student working for Leighton, right? Leighton is one of the best guys, one of the best my friends. Right? So, and you work with those coolest guys in the world, you're going to get better. Right? If you work in Microsoft, you probably earn a lot of money, but you know, you climb up the ladder pretty hard. So, and AI PC, I think, is one of the things is all about agentic, how you're going to generate contents, right? And basically, we're saying that if you're now in the school age, you were saying that how we're going to make a better teacher or professor, right? So, you can think about that. But for me, I'm living in Europe. You know, one of the problems in Europe is what? The parties speak 40 languages, right? And I decided to live in Switzerland instead. I need my kids master German, High German, French, right? Swiss French, Italian, Swiss Italian, right? And then English, and you know, mixture of English. Right? So that is why I say that a content is very important. I want later on, well, I want my application, my laptop, my earpiece. Whoever speak me language different, I just want to listen to my English. That is, I say, is very important. And then web application, I guess, yes, a lot of agentic applications. And coding is already, you can see a lot of startup on the coding side is worth $10 billion. Whether they can get rid of software developer, I don't know. I hope so. So that means that don't be a mediocre software developer. You better be the best, okay? And same game, I think most of the game gonna make by AI very soon. So 20 probably, you know, used to be 100 people, probably now you need 20 people to make games. So and the developer, we're going to saying that we're going to do some API on the browser, right? Oh, sorry. And then we do similar to web. I'm going to talk about it in the law of American Summit. You do watch our news. How do we do it? How do we bridge the browser can use RISC-V matrix APIs, matrix APIs and assemblies. So the challenge of RISC-V SoC, as I say, there's no unknown market, and the required power unknown, and resources unknown, and not enough people, not enough time. Tell you why we not enough time. Because of 15 years, DeepComputing is the 4th year. We don't break even, then we broken. So I said to Jonathan, we lose $1 million every year. If this year we don't break even, next year you won't be seeing me. Yes, and then so if you want to do RISC-V, buy some of our motherboard, buy some frameworks laptop. So keep us survive. And then we survive, SOC guys survive, and sci-fi survive. Otherwise they're harder. So and AI is very difficult actually. You know, before AI is those small model, and then now transfer to transformer, and then have DeepSeek, all these things they are changing, and the framework is complicated. That's why who does monopoly the whole market? Because all the AI framework, the first hardware they put it to is CUDA, and those framework have no enough resources to put it to RISC-V or other AI. Hey, come on in. You want to come in? We're busy. Come on in. People don't wait. Come in. And what happened is that, so all we like RISC-V, you want to do hardware, we have a porting optimizing. That's why if you guys have try to learn AI and become a good AI developer, not those normal application developer, gonna join us some of the open source program to help to optimize the libraries. So join our open source project, and later on Google my name, find LinkedIn, connect to me, and then we waiting for my news to open up all the open source projects. So, and how do we make it faster, successful? We send the hardware guy using chiplet. So this is a classic. For example, for our laptop here, the second generation framework RISC-V motherboard, we have two chiplets. So it's one chip is here and another chip here, and then you can both chip connected together, it becomes a core. And then with a mini desktop, we have coming with 10 of these chips. So once you build chiplet, that means that people can scale. That's exactly the way AMD beat Intel's, just like that as well. Your PCIe as well. You can see this is just not, it's a 10 chips. Put it as a PCIe card. That literally can run one car, can run, we guess can run 671B model in Q4. Model. So that is, and the other thing is that you can make it as a motherboard, you can make it a PCIe card. So it's very flexible. So I'm not talking about a lot of things now. For through, we partner with a framework. Then we're going to talk about framework, how good they are. So and you can see I do more promotion on RISC-V on framework than RISC-V. You can see we can do a lot of fun things. It's open hardware, right? So RISC-V is good. We partner, everyone opens. So this is the motherboard we make for framework. So it's the coming framework. It's only $300 for the entry versions. Then you can have a RISC-V motherboard running laptops on frameworks. And more than that, we're gonna make the AI PC super LLM machines for their desktop. So you can rack it up and you can make it as the professor, put it into the lecture rooms, and you do better than, answer better than the professors. So that's about it. And this is a monster machine with x86. I'm not 100% we're gonna make it yet. We might make some prototype. And you can have x86 or ARM and RISC-V at the same time. So this is a 16-inch, but it's very expensive machines. Okay, so the roadmap is just something we're going to do, and we do have 12 to 16 core motherboard coming out as well beside the 8 core. So look forward to you guys. Thank you.
Thank you.
Happy RISC-V. So RISC-V is in this age before it bounce back.
Hello? Okay. This is my talk. I'm from Framework. I will talk about why we sell a laptop, an empty laptop without a mainboard inside. A laptop that you cannot use. That's not doing it.
Yeah, it's scam.
Yes, I am Daniel. I work at Framework. I live in Taiwan. I do software, firmware, anything code related at Framework. Framework, we are a new small computer company, just 5 years old. We're just about 80 people, mostly in the USA and in Taiwan. Here we do most of the engineering and the factories here. SMT is here in Taoyuan. And we're trying, just like with RISC-V, we're trying to also change the industry to make the hardware more friendly to users. Last year we had only 2 products. We had just the Framework 13 that I see a lot of people have in the room. And we just came out with the Framework 16 last year, which is bigger, has also a GPU, and exchangeable, easily exchangeable keyboard that runs open source firmware, QMK on the keyboard. This year we have 2 more products, Framework 12, which is smaller, lighter, cheaper, very durable, made of plastic with rubber, and it has a touchscreen, stylus, and also a small desktop that's super powerful and can run games and local AI. And you can see it downstairs. And just for the size comparison.
I thought you were selling the Ludo as well.
And the main topic is this. So on our website you can buy an empty laptop.
Well, this is expensive.
That's Taiwan dollar, right?
Yeah,
Oh.
of course. Well, let's first talk about what we do. Like, we make repairable. We always say repairable laptops. Why is that important? Like, if you buy a MacBook, it's screwed and glued together. It's very hard to open, and if something breaks, you basically have to pay up a lot of money. We want users to figure out themselves, to be able to. You don't have to. You can send it back to support, but a lot of issues are easy to diagnose yourself. Or if something small breaks, you can just, if the screen breaks on the framework, if your cat chews on it, there's no need to have a big expensive fix.
Yeah.
You just buy a new screen. It's 4 screws, anybody can do it. And we have guides for everything. Yeah, it saves everybody money, it saves the planet, and it's a good idea in general.
And you know the record is it? It's a 10 years old girl, my daughter, using 5 minutes to swap a motherboard. So you guys can.
5 minutes is good. I can do 4 minutes. Yeah, so we publish a lot of guides to help people. Every part has a QR code to help you find out how to exchange it. And we also have a good support. If people have problems, we help them. And we also host a forum where our users can discuss ideas and help each other, and we help them too. Every single part is user serviceable. There's nothing glued in. Anything you can replace yourself, or if not, you can send it back or ask somebody else to make it. And every single part you can buy from us. So maybe people replace the battery on their HP, but often you can only buy it from some aftermarket, some shady websites. Yeah, even the mainboard, display, keyboard, screws, you can buy a bag of screws, or hinges. We have a stronger hinge if you like your screen to bend more strongly, you can buy that. And we publish some limited schematics, but to many repair shops, they can get the full schematic to repair it, repair even the traces on the mainboard. Yeah, like I said, nothing is glued in, especially not the battery. Screws for everything, and most of the screws, they even stay in. You can't lose them, they don't fall out. And if you buy the laptop, you get a screwdriver with it.
Yeah, I suggest you guys go down to the pool and try to break it.
Yeah, and if you do lose some of the screws, there are extra screws in the case. Right, instead of glue, we have a lot of magnets, so it holds together by itself. And the connectors, like you said, you can try to break it. If you want, you can break it, but normally it's not as easy to break as some other. I disassembled my other brand's laptop and just one time taking it apart, the connected racks. And most components are socketed, like the RAM, the Wi-Fi, the SSD is not soldered on the board. You don't have to buy it from us. You can take your own or upgrade it. And then if you upgrade something, the parts that you got extra of, you can reuse them. Like the mainboard, you can just run by itself. You can re-pin your case and just plug in power, screen, keyboard. And because we published the interface specifications for everything, some people even made adapters for our display for the keyboard and reuse them in many creative ways. For the mainboard, we partnered with Cooler Master to just make a case for the mainboard, and you can put it behind your screen and use it like an all-in-one desktop. Let's skip this. All upgrades are compatible in both directions. So if you buy an old laptop, you can keep upgrading every generation, or if you have a new laptop, you can put old mainboards inside there, and everything is compatible with each other.
The life cycle is 7 years.
Well, the company is only 5 years. We have no plan to change that. Yeah, here's some examples of the parts. Let's skip this too. Right, another idea is open. Anything, everything, we try to be as much open as possible. So it's your hardware, you buy it. We only make money from buying the hardware. There's no reason for us to control what software you run on it. Like Apple, they make good hardware, but you're forced to run whatever software they want you to run. Yeah, and so you can run whatever you want, but we also help you to run Linux and other open operating systems. And people think it's hard to make Linux compatible hardware, but actually, if you just care about it a little bit, most vendors don't care about it, but for example, the fingerprint reader on many other systems does not work on Linux. But we just chose one that's compatible already, and then everything works out of the box. And a little bit we work with the silicon vendors like AMD, Intel to fix some bugs, and sometimes we have to do small workarounds, but it's pretty simple. LVFS is the method to update BIOS and firmware on Linux. And we release everything on there, and it's even easier to update on Linux than on Windows. You just get it automatically. Yeah, for some of the components that are not the BIOS, like the camera and the touch screen, I push changes to the open source project to help us update.
So the MIP 6 is also pushed.
Second?
The Intel MIP 6, their camera.
We just use a USB camera.
Oh, just a USB camera.
Yeah, that's much simpler, and it works on everything.
Yep.
Yeah, you can use whatever distro you want. We don't. We test a few. We have some suggestions, but we don't really care as long as it's up to date. Anything can work. Here are some projects that our customers have done. So because we publish a lot of information, people can do many different things. It may not look like it, but it's got the same mainboard inside that we have in the laptop here. And somebody put a small keyboard in the screen that runs Ubuntu. Or somebody made a tablet. They 3D printed a case and took a Type-C touchscreen and fit it all together. And it works like a tablet. Or somebody took just the mainboard, 8 of them, and 3D printed a cluster and just exposed the Type-C ports, and you can have a powerful data center at home. Or here, a mechanical keyboard with a mainboard inside that you just need to connect to a screen and power. People always ask us to make many different things, but we can't make everything. So we help.
And it is better than the cooler mask.
We help.
And let's make it mass produced.
Okay, let's get back to the main topic. So we sell it in a few different ways. You can buy it just pre-built. We say you can repair it, but it's just a normal laptop. You don't have to open it up. You can throw away the screwdriver. You can buy it with Windows and give it to your mom. But you can buy DIY and assemble SSD, keyboard and RAM yourself. You can buy them yourself. You don't have to pay us for it if you have a cheaper supplier. We don't care. We make our own hardware. That's what we make the money from. And you can buy the mainboard only. That's mainly if you want to upgrade, or you can just run the mainboard by itself. And now recently we introduced the empty chassis without any mainboard. Yeah, this is one of the mainboards that we sell, and then this is a different mainboard. So this laptop looks the same as my laptop, but it's got this different mainboard in it, and it looks almost the same, but it's not made by us. It's made by DeepComputing, and we didn't help them very much. They use the public specifications of our connectors. So Type-C is pretty boring. It's just you need to put it in the right location, and then we have the screen connector, camera, fingerprint keyboard, and so on. So we publish all of the information to make your own. And DeepComputing made it, and then they came to us and said we should partner and sell it together. This is one example of what we publish. So it's all of the components and how they're connected to it on our mainboard, and then DeepComputing can reference that and make their own. Here, this is the interface for the touchpad and keyboard. And yeah, DeepComputing, they just made a connector on their mainboard that does the same. And that's pretty easy because the keyboard is just GPIO, and it's controlled by the embedded controller, which we publish the source code of. So DeepComputing they reference that and implement it. Many vendors say that the firmware has secrets, that they cannot publish it because there's some secret magic. They do some very special things, but in reality it's pretty boring.
Quick work.
Touchpad also is very easy to make work. It's just connected with I2C to the CPU and uses HID protocol. So the kernel has a very standard module that you can compile for any architecture. So even on RISC-V it works without any problems. The fingerprint reader is USB, and there is a user space library and software for it. So they only had to compile it for RISC-V. And they asked me for help, but I think it was pretty easy. Display is connected with the embedded display port. So I think their SoC does not have the display port, so they had to use a DP to HDMI converter to make that work. Camera is USB, so USB is already supported for RISC-V for generic devices, and the kernel has a generic driver. For microphone, just like on our mainboard, you need a codec that connects to the CPU and has a very standard kernel driver. And Type-C, for the user it's very simple, you just plug in Type-C, but actually in the hardware and the firmware it's a bit more complicated because it can do so many different things. So for the charging, you need a PD controller that handles all the logic. And if you want to support display output, it's using DisplayPort's alt mode. And again, for that, they need the 2 HDMI converter. And because the Intel and AMD CPUs, they have a lot of support for many different displays, but the old RISC-V chips they don't, so only one of the ports support display output, but upcoming RISC-V chips, I think they can support much more. Yeah, in summary, it's challenging to build great hardware, but we've shown that it's possible, and that also other companies can work on at the same goal. You can find more information on our website, or find all of the references that I mentioned on our GitHub. And you can find us on the 3rd floor, or talk to me here afterwards.
Yeah, just follow them.
So, Mr. Sergey, and let's welcome our next speaker from ExpressVPN, our slide. Oh, Plantian. Plantian bound phrases.
I couldn't help but notice the room just emptied. I'm not sure if that's a reflection of my talk or how good the other talk was, so but we'll go with that.
No, I think it's because getting bored. So it's our fault.
Can't blame me this time, I've only just got here. Cool, so at ExpressVPN we've always been very strong on privacy and transparency. And more recently that's meant we've started looking into and digging into open hardware. Now we've looked at this in the past, but it's only more recently that we've been able to really kind of get to grips with this. And I think it was only a few weeks ago that we finally completed the paperwork, and we joined RISC-V International as a strategic member. So, we've heard a lot about RISC-V as being very open. We've heard about that we have the framework that its modules are easily comparable. What if you do that one step further? What if you could verify every layer of your stack? And by that I mean all the way from the silicon to the software itself. And at Express, our transparency philosophy is pretty simple. In order to get transparency or provable transparency, you need to have a number of things. And in this case, to build trust and to ensure that we actually have a platform that people want to use and that we can demonstrate that we do what we say we do, we need to be transparent. This isn't as common as we might hope, but with the work that we're doing, for example, Lightway is our main VPN protocol. It's open source, anybody can download it. It's had 2 independent security audits on the new Rust code base. The previous C version also has full security audits. So open protocols enable verification, like they're there for anyone to check. And it's the open infrastructure that enables trust. So what exactly does open hardware enable? And the answer is really new possibilities. There's a lot of interesting stuff that you can do once you can actually get hold of the hardware itself. And so this is just talking a bit about what we've come across so far. We're pretty early into the journey, but I thought it was still interesting to share. So for us, so Lightway, as I mentioned, is fully audited. It's open source. Anyone can get hold of it. Trusted Server is our in-RAM operating system. Basically, we deploy it directly to memory. It never touches disk. If a server is unplugged from the wall, everything's gone. You plug it back in, it's exactly the same as when the data center handed it to us. We don't install anything on the boxes, we never touch the disks. That's in progressively open source. And our next frontier really is the hardware. That's where we're headed next. And once we do that, we complete the transparency stack. So right now, applications, protocols, operating system, all available. Firmware, not so much. Those are all black blobs in most cases. And the hardware itself, still not there yet. That's still undecided. And that's something we're hoping that RISC-V will help us with. So why does it matter? The challenge is interesting. Off-the-shelf hardware is designed to a price point. It's designed for a general user. It's not designed for privacy. That was never one of the considerations. Many have black box components, which means the capabilities of those things are unknown. You have the capabilities that they claim are provided, but in reality you have no way of knowing if that's true or not. I'm not saying that's a conspiracy theory, there's probably nothing in there, but you have no way of knowing. Just trust us, I'm sure it's fine. Never heard that one before. It's also limited flexibility, like one size fits none. This usually means that if you ever, in my experience, whenever I bought a new machine, a number of times I tried to do it properly. I've been good, you know, I want to save money, I'm going to buy the right machine for me, I'm going to get the right amount of memory, I'm going to get the right CPU, I put all that effort in, I buy the machine, and within a week, it's not good enough for what I need. And I should have bought the bigger one after all. And now I have no choice but to either live with this mistake and be miserable for the next 5 years, or go and buy the one I was going to buy originally. And this is one of the problems. You really can't tailor things too much to your needs. This used to be true for laptops, 15 plus years ago, where if you wanted more memory, you could have it, but the hard disk was smaller. Get a bigger hard disk, less memory. Why? Who knows? But that was what it was like. We have the AI privacy dilemma. I mean, I'm sure you've been to the AI talks here, and you've used it all yourselves. I mean, if you use any of the cloud AIs, they're extremely powerful. They're extremely quick. Private, not so much. And it was really only after a lot of people complained and businesses refused to use it that the big AI companies even started putting policies in place to say, okay, we promise we're not going to basically steal your data and train on it. Which is important because often that data turns up in other people's answers, which is not really what you want. Now, despite how powerful this stuff is, a lot of people have questions that, oh yeah, AI would be great for this, but there is no way in how I'm typing that into ChatGPT. Right? I'm not putting that into Claude, because I'm just not going to do that. But that's okay, because we have local AI, and it's private, but that's pretty much where the good bits end. Even if you get one of the larger models, like for example DeepSeek, it doesn't compare very well when you run it locally to what you can get hosted. And obviously there's very simple reasons for that. It's just they're running on better hardware, it's more optimized, they access more resources, and they have the benefits of scale that when you run on a local machine you don't. And of course, it's usually slower on your machine because you don't have a massive data center in your pocket. And this is something that custom hardware could help bridge. If you had something that was just doing this one piece that you need, and only focusing on that part, then there's a lot of potential wins that you can get out of it. It also extends zero trust. I mean, historically it's always been don't trust the network. With SaaS and things, now it's don't trust the service. Potentially in the future, then we're looking at trust the hardware. Now, this has been tried many times. I think the one that got close to it was open power. That's mostly in larger servers, didn't really go very far. But it was never something that you'd expect to see in a desktop, let alone a laptop, and forget mobile, that's never happening. But if you want to trust the hardware, you need to be able to see what it's doing. Now, this is a bit like open source. The fact is you can go and check. I mean, it doesn't mean you will, but you could if you wanted to. And everybody kind of hopes somebody will go and check it. But it's much harder to hide things and to be non-transparent if anybody can go and look at what you've done. It also changes the dynamics of how you do interactions, right? So for example, if you look at, again, Framework's a great example of that, their stuff is all open, right? You can go look at it, you can discuss it, you can criticize it, you can do, you have these conversations, but it's all there. And the beauty of that is, if you're doing a great job, that shows up too. So it cuts both ways. So what are we learning from our initial run into this particular field? Well, RISC-V, it's not just open, it's customizable. Now this is of interest to us because we have a lot of things that we specifically need for our use case, but we don't need anything else of it. So we saw this, for example, when AI first started getting big, and people started buying, basically, big, heavy-duty GPUs. And it wasn't long before you could get a GPU out the actual graphics adapter on the back of it because no one was using it for graphics, they were just using the cores. But in those cases, you got the adapters because that's what you got. There was no way of getting rid of it. You just had to work what you were given. And that adds cost, it adds complexity. So if you only want one tiny piece, you don't have to bring in the whole shop. And that's something that RISC-V will let you do. It also, again, goes in both directions. You can add the things that you care about, and you can remove the things you don't. And you can optimize your use case. And this is pretty much purpose-built for privacy, right? You can customize this whichever way you want. There are open source GPU cores you can already download. You can stick on FPGA. There's a great device created by Bunny out of Singapore, where they have, he's created a RISC-V processor that runs on an FPGA inside the device.
I don't know the device you're talking about.
Yeah, I've just blanked on the name of it as well, but it's a lovely little device. But he's already got the code so that you can go and verify that the CPU that you're running is actually the code you think it is. And so you can be assured that your processor actually is what's claimed, and you can go look at the code and you can see how your processor is built. And of course you can change it, fiddle with it if you want.
You're talking about it, the precursor.
Yeah, the precursor, yeah. So it's a really cool device that even in the background adds wiggly lines to help make sure that nobody can do inference and stuff on the screen itself, which is kind of neat, if you've ever come across the Tempest. So what do we discover when we're doing this? Well, things are moving really, really fast. When I first started looking into this, there wasn't a huge amount, and I started collecting little RISC-V boards. I'm going to have to kind of get out of that habit now because, well, one, there's too many of them, and two, they're getting more expensive and more powerful. So it used to be just a cheap thing you could pick up. Now they're getting a bit more expensive. Support for these things is massively expanding. Previously, when I was first playing this, there's a lot of work to even get the thing to boot or to do anything useful. But today, that's completely changed. Now, for example, if you run the Orange Pi V2, it runs Ubuntu out of the box and it works beautifully. Everything works. Performance, not so great. But again, like the first laptop I had was so slow that you really couldn't use it. It worked perfectly, but it was just too slow for daily use. But the fact that it actually booted at all was pretty cool. A year later, now it's completely usable. The one that's just come out, yes, it's not as good as my x86 laptop, but now I don't feel the need to throw out a window constantly, most of the time. Right? And this is in like a space of like 2 short years. We've gone from an unusable prototype to I can actually use this, as a daily device. I can actually develop on this. In 2 years, that is huge. Hardware in particular doesn't normally move that fast, and so to see this massive step forward and then have this huge support behind it, it's huge. Early days, there's still limited options. Standards are evolving, but that's part and parcel for the speed that we're moving at. So we're building and testing on RISC-V. We're playing a few different proof of concepts, particularly like VPN acceleration, stuff like that. Lightweight works in a very particular way, and so if we can get that on chip, or get that closer to silicon, then we can potentially speed up the VPN, we can lower the overhead, we can use less battery and all that sort of stuff. Of course, it has custom extensions, so if we do want to do interesting things, we can effectively add that to the chip itself. So why are we really excited about this? I mean, for example, if we build a VPN router with this thing, where every component is audible, the hardware acceleration actually works, and it's transparent, and it doesn't need a special kernel from 30 years ago, isn't using an old SDK, is modern and fun to work with, where there's no hidden management engines, and you control effectively the entire stack. Then you have true end-to-end transparency. From that you can build trust and you can build your privacy. Privacy preserving at the edge. Again, imagine you have this as a router device and you use it for get to your storage. Imagine if you could do limited AI workloads. What if you could tag images or create subtitles or do translations for the videos that you download? All these background tasks that don't need super performance real-time response. I can sit away happily working on this. You don't need it to be instant, but now it's on your device. It's running on a chip that you have the specs for, running a hardware that's vetted and open. You basically get all the power of AI, but you also get the privacy protection. Now, it's never going to be quite as good as what you're going to get in the cloud for fairly obvious reasons, but you just need it to be good enough. You need it to hit your use case. And there's some very compelling things that we're already seeing you can do with this. Trusted server 2. So right now, for example, as I mentioned, all of our servers, they run on RAM already. All of our images are cryptographically signed. Every server runs exactly the same image. There's no difference between any of them. And we have a lot of transparency and trust that kind of built into this. But it's only from the OS up. We can't work down. And what would be really cool is if we could have servers where we actually control the whole stack, where we can validate the server is the server we think it is. We can validate it's running the hardware we think it's running. We can validate that no one's start plugging things in and playing around with the thing, which is obviously for our use case extremely important. But this is a step forward that with current stuff like the x86, there's never any way to kind of prove this. You can do some stuff like say SGX and stuff, but then again you're still trusting that CPU implemented correctly. Spoiler alert, it doesn't, it's been broken many times. We need other options basically. So transit opportunities, yeah, these are, I'll go through these quite quickly. I mean, as I mentioned, it's not yet up to speed, quite literally. Tools library is still developing, limited vendors and options, and new skills and knowledge are required. However, it's realistically only a few years that this level of performance and hardware has become available, which is still insane to me. Like, I mean, I remember waiting, well, literally a decade for previous, like Open Power, for example, is literally 5-10 years of work. We've gone from something that's unusable to almost something you've got server grade in a very short space of time. So this is expected. If we didn't have this, then it would show that no one actually cares about it and no one's actually getting involved, which would be a much bigger problem. Some core opportunities though, freedom to innovate. We don't have to be constrained by legacy design, so you can basically do whatever you want. And again, with access to things like AI, with access to things like YouTube, with online stuff, the communities, you really can start building the stuff yourself. You can take a basic chip design, you can synthesize it onto an FPGA, you can make tweaks and actually play with it. And if you can get design work on an FPGA, then it's not too hard to get at something you could take to a foundry. You probably shouldn't, but you could do that if you wanted to. The community is amazing. Everyone's kind of interested in this stuff, has rallied around it surprisingly quickly. It's just a good idea, and it's relatively rare that these things turn out. Usually there's always something for someone in it, and someone somewhere is kind of getting screwed over. In this case, everybody wins. There's no downside to this. You still have the first mover advantage. We're seeing people creating some working with this, and we're already seeing companies kind of probing around to see who knows a bit about RISC-V, who's doing stuff. Right? I'm already seeing, because I mentioned RISC-V, I'm always seeing people like scouting through my LinkedIn profile, just because I put that sort of stuff on there. And differentiation. If you have your own chips and you're doing your own thing, that's something your competitors can't match, right? They don't, unless they take your chip and they run your chip, which honestly would be amazing. If our competitors want to run our stack, please feel free. That benefits us. It benefits their users because we feel we have better stacks. Of course we do. And truth is, I'm pretty sure we do. Not biased at all. So from our point of view, it's a win. They win, we win, everybody gets something better. And if they improve it, well, we'll happily take that too. Right? So this is a very interesting dynamic. It's very rare that you can actually both have something that has no differentiation because everybody can use it, but that itself is your differentiation, that everyone can use your tech and benefit. Right now this is very rough, but yeah, I reckon prototypes 1 or 2 years for like some of the serious stuff that we're talking about, products 3 to 5, and then like starting to see real standardization. We're already seeing this, like the early stages of it. The framework itself is actually in place to make this happen. It's going to take a few iterations before we do it. And again, we're talking about hardware designs, chip designs. Like 5 years sounds like a long time, but bearing in mind, like ARM and Intel come from the 80s, and how long it took them to get anywhere near what we have today, and you realize that RISC-V is actually moving insanely quick. Time to start exploring. I won't cover this too much because you guys probably already know this stuff, but just pick up a board. If you go to AliExpress, for example, there's a whole ton of stuff. It's really cheap. If you don't like buying from them, you can buy from effectively a reseller. But you can get boards from just a few dollars basically, all up to like the heavy duty boards like the Orange Pi if you want. For porting your software, most things do just work. Not everything, unfortunately, but a lot of it will just happen. And work with the community. There's a lot of stuff out there that's particularly that we've come across where someone else has hit the landmine before we have and has reported back like, do not step here. Beware. And start small. Have a play with it. Like, it doesn't have to be perfect first time. Just get some experience with it, get used to it, and then give that feedback. It's surprising how just a small amount of feedback, a one line in a blog, or a reply to something on Stack Overflow, can really save someone else potentially days of work. And yeah, it's better we're together. It's not a solo journey. I mean, the hardware guys, they need use cases. Software developers need the hardware, and everybody else needs solutions. Basically, no surprise there. Open source community, we all need each other, and it's just better if we work together. Everybody brings their own abilities to this, and we all walk away with something. The sun is great at that. Whole is great in the sum of its parts. So why does it all matter? I mean, for us, obviously, it's VPNs, but it's about building infrastructure that we can trust, and I mean that term in a very generic sense. Wherever you use this, whether it's in cars, whether it's in machinery, whether it's in technology, it's all about that. It's also about having options beyond big tech, right? Right now, this is kind of concentrated to 2 or 3 very, very large companies, and we've all seen with the complex geopolitical stuff going on, things that we assumed would just be, the way things always were, have suddenly not been the way they always were, and that's left entire industries and countries looking for alternatives, and there aren't any because nobody thought this would ever be a problem. So having options is always important. You can innovate without permission. You can just do what you want to do, and if it works, it's great. If it doesn't work, well, no problem. You can always try again. And yeah, I think it's the future of digital privacy, the ability to know that what you think you're running is actually what you're running. And to put this into context, I mean, Red Hat did a very nice promo video for this back in 2005, something like that, called Truth Happens. It's worth a watch if you haven't seen it. But it's really interesting how Linux went from, this is just a hobby, to in 2000, which is when I got my first Red Hat Server Engineer qualification, which I realized when I worked that out was about nearly a quarter of a century ago, which is quite disturbing. But back then it was very much a punt, it was a guess. And nobody was deploying Linux en masse. There were no smartphones, there was no Android, right? It was servers, that was really it. A few of us had laptops, but Linux on laptops was not such a great experience. 2010, Linux was definitely in a very, very strong position, but it was still the case of, it's great for these things, but if you want to do this, you still need this other stuff. And 2025, there's a very rare reason why you'd ever boot up a Windows server. So I think RISC-V is on the same path. I imagine that you will see the same sorts of thing, this is a toy, no one's going to use it. Oh crap, people are using it, but it's probably not going anywhere, it's just luck. And then by the time you actually realize, no, it's a thing, you're now 10 years behind and everybody else is ahead. You can see this, for example, with NVIDIA's recent announcement for RISC-V support, and that's really cool, but in the long term, I don't think it means anything right now. But they're making the bet that if this thing gets big in 5, 10, 15 years, we want to be there. We don't want to be the ones that thought it's just a toy and it turns out it's going to change the world. Because nobody wants to be left behind. So even if people are only getting involved just to make sure that they don't get left behind, and possibly because they're trying to make sure that they don't get left behind, it actually drives the thing forward, it's all good. It's not the whole solution, but it's a big piece. Combine that with open protocols, try that open software, bit of engineering, bit of visualization. You can build yourself your digital future. And let's discuss. I mean, if you're interested in reaching out, I've got my LinkedIn there. I think I've got still got 5 minutes left.
Sorry?
So I have a few minutes left because I'm.
Oh, okay. 7 minutes left.
Cool, because I've got my colleague Ben.
Just this quick.
Yes. Do you need the slides?
Yeah.
Cool. So you plug that in. So Ben's an intern at ExpressVPN. He's only joining us for a short period of time before he has to go back to school. So he was with us for 3 months. And we said, well, we have this school project that you might want to do for 3 months. Is it working? Yeah, need to drag it. There you go. And so we have this interesting project. Have you ever ported software? No. Have you used RISC-V? No. Here's an interesting board for you to play with.
Yeah, so hello, I'm Ben Ho from ExpressVPN. I'll be staying, I worked here for around 3 months, actually 2 months, a bit more. So my job is to port the lightweight protocol, the open source VPN protocol to RISC-V. So this is my journey. From a software developer perspective, I know nothing about hardware, little about hardware, but I am successfully ported it. So I will sharing my journey. Few talks. So basically, many software developers, they don't understand that CPU actually still have their own languages. So we call them ISA, right? We'll have like the traditional one, like 86, ARM, and now we call like the RISC-V. So I skip this one if I like. Yes, yeah. So RISC-V is basically an open source ISA. It's a free open source and modular alternative to 86 and ARM. Yeah, skip this one. This is one out of time. Yeah. So first of all, yeah, it have like permissive license. This basically, I think this is very important in a business perspective. Because of this permissive license, business can actually make RISC-V cores without much license fee. It reduces the cost, and it's very benefiting to most businesses wanting to make their own cores. Secondly, it's modular. So basically, if you have some specific use case, for example, hardware acceleration or like matrix multiplications, you can implement your own ISA and tell a vendor to just make the course for you. And because this is a RISC structure, so it's very simple to make the silicon as well. You only have like less than 50 instructions compared to the 86, like 886, which have like 1,000 instructions, which is so difficult to make. Yeah, and lastly, it's open source. So I come from the software stack. I'm a software developer. So basically, I guess most software developers cares is the adoption, like how easy it is to build business applications on top of this stack. They don't care about like what microarchitecture you use. Like how can I as a business owner make this work? And I think like most hardware developers, they forgot about this. Like we need to start at the very bottom and go up in the stack to make the adoption really fast. So where are we now? There's growing support for RISC-V. So basically at the bottom we have like the QEMU emulator, the containerizations, and all these are well supported by now. And now we got like operating system like Debian or Ubuntu. They're all here as well. And now we got to the upper part. Basically this is the language support, the compiler supports, the runtime supports. These are all the lacking right now. I think we should be working at this level right now. Also like the Docker as well. Because Docker now there's a lot of like, there aren't many RISC-V Linux, RISC-V Docker images. It's going to cause problem later. So I'm going to share my experience, like short 2 months experience with porting to RISC-V. So basically, if you're writing a Rust project, good, like you're in luck because it's very easy to port to RISC-V. You just ask the argument 99% of the time, it works. Except if you depends on some weird like inline assembly, then you might need more effort to rewrite the assembly. The good part, another good part is that there's growing communities. So if you go to GitHub and you're going to find so many people talking about RISC-V. I see RISC-V support on like discussion on like Node.js, Deno, a lot of, even I already have one. So you're basically and lastly, you can always build your applications if you cannot find official builds, build from source. It's usually just one. So, but it's not all rainbows and sunshines, right? We also like have a lot of other problems. For example, like the first one is a lack of available RISC-V Docker images. So any serious project will have like CI/CD of some kind, right? Sometimes automated testing, sometimes containerizations. Without Docker images, it's really hard to justify this to a business owner. Like why should we like move to RISC-V when there's no clear benefits? But it's so hard to do because I have to like rewrite all Docker files. I have to rebuild all the Docker images. It doesn't make sense as a business owner. So I think we have, if we want to like adopt RISC-V in the future, we need to solve this part first. And lastly, secondly, there's basically no remote debugging tools. A lot of businesses, especially the higher level one, they depend on like VS Code. A lot of people use VS Code, right? You can't even run SSH to a Tiger machine running RISC-V using VS Code. That's already like kills 50% of the developers. And lastly, GUI application is really lacking the support. So I guess most business owners, they have some kind of like GUI applications, right? Even our own ExpressVPN, we also have like GUI applications on Linux. We use Qt. But Qt, there's no official support for it. It really slows down development for like a month, and it's going very slowly. Actually, I'm still not able to get it running. So yeah. So where are we now? ExpressVPN and RISC-V. So basically we have successfully ported the Rust implementation of VPN. So basically that's the lightweight to RISC-V. I done that in the first month in the internship. And it's because of Rust, it's partly because of like all the CI/CD and like cargoes so easy to use. That's another reason to use Rust, by the way. Yeah, but lastly, the GUI and users clients are still in early development because I'm still trying to get Qt and to get Qt works. So how do you prepare your project for RISC-V? So firstly, you need to understand your tools, okay? Select your tools, change them if need. And you need to start writing tests. Absolutely, because we have encountered some cases where the program compiles, but something doesn't work. So when you try to, you have one instances where the 4096-bit certificate doesn't load. Okay, we have spent like not years, but like weeks trying to figure out what happened. The test passed, for example, but it doesn't work in production. Okay, turns out there's some problem in our test, but we have fixed it. I have fixed it.
How many slides do you have left?
Yeah, and lastly, if you use inner assembly, check if it's really needed, and ensure compatibility if you want to migrate to a new architecture in the future. So yeah, I guess this is short. I'm not rushing. Yeah, thank you, everyone.
And then we also work with a lot of different partners in the ecosystem to make sure that Ubuntu is the preferred platform to develop on, right? And this is like taken from the example of like AI, where we work with different developers from both the cloud down to the hardware, and also from different industries, different verticals that also leverage Canonical as a key open source supplier. So what does Canonical do on RISC-V? We're actually a large player in RISC-V. And we started, our journey began about 4 or 5 years ago, where we started making Ubuntu available on the first few RISC-V platforms. So our mission for not only for RISC-V, but like for all the different ISAs that we support is that we want to make sure that open source is available on any architecture for you to do any tasks, and you could do development on such as your enterprise workloads can all be supported on Ubuntu. And we do this through collaborations with partners. In the past few years, we've worked with a variety of partners, and I'm listing a couple here that we worked with recently. At the beginning of the year, we worked with, say, Sci-Fi. We got Ubuntu running on the first development board that's being powered by P550. That was a really big news for the community, as Ubuntu is a preferred platform for developers. But also we worked with companies like Ventana to enable like high performance computing on their systems, right? And then with DeepComputing, where we've been good partners with them for the past few years. And then this year we've launched, we helped them launch a new laptop, this BC Roma with the SWIM computing chips. And then also back in May during the RISC-V summit in Paris, we also worked with SWIM to enable their EIC 77 series, the new chip that they have. And then we demoed how the DeepSeek is running well on the platform as well. And then we also collaborate a lot with the community, right? We joined the RISE member back in 2023. RISE is a software group that works alongside with RISC-V International. And then we're also part of their one of their communities, and we also have a share on that as well. And we're also very prevalent in the different summits. All the big summits we also try to take part in. Like this year, we're also going to the RISC-V North America Summit in Santa Clara in October. And then we've also participated in both the Paris Summit and then recently, last month, in the Shanghai Summit. It was actually one of the first summits that we went to in China, and we got really good, we were received really well over there because people in that community didn't really know what we were doing, and they were excited how Canonical, especially Ubuntu, is being made available in China, and we're committed to supporting the ecosystem over there. And then also, we ourselves, we host a Ubuntu Summit every year, back before, but now this year, we're switching the way how we do it. We're going to host a Ubuntu Summit twice every year now. But here, I want to show a couple of cool things that we've done for RISC-V, where Narav, the CEO of Framework, was performing how he could swap out a x86 motherboard to a RISC-V motherboard just under 5 minutes, right? So it seems like 5 minutes is a benchmark, right? So I see if anybody can do it quicker than that, right? And then also alongside Yuning, alongside my colleague Gordon, they made a talk about how making sure that there's a commercially ready Linux is very important to the RISC-V development system ecosystem, right? So that was really well received as well. Both these talks are actually on YouTube. So if anybody here are interested in seeing this, they can visit YouTube and take a look on that. The framework one is actually really well received. It's got like 20,000 views on there, so highly recommend. Yeah, so in addition to that, we're also working continuously with the different hardware vendors, SoC vendors, to make sure that Ubuntu is available on their platform. So on our Ubuntu.com website, you can see that there's a lot of different hardware platforms that you could download Ubuntu images for. As of now, as you can see on the right-hand side, these are most of the images that's actually directly available from Canonical, but there's also other ones that are hosted on our partner websites, like the S-Words, and also the Orange Pi, for example, also has images available on their website. But in the future, what's going to happen is we'll try to centralize the ones that are built the way how we want it to. Like there's a certain tools and processes from Canonical to build Ubuntu images. If you follow those rules, then we will host that onto our website. Or if you upstream stuff into the mainline, we can also build images for you, right? So we could, and from there, we can host it onto the website, and then people users can know that these are some of the official images that are being recognized by Canonical, and then your users can come over here to download it. But I think over here, what I want to also say is that we're also looking out to make sure that Ubuntu is available to as many of the developers as possible on RISC-V. So if you know of any platforms, or if you yourself are developing something and you want to on your platform, please feel free to reach out. We're always looking to work with more people. We want more people to use the operating system, and we're here to support this. We could host your image. We can also make PRs like what you see on the other side, where we help SWIN and back then Orange Pi to promote their platforms that Ubuntu is being the preferred operating system available on the platform. So do reach out if you know of anybody that needs this. And then on the other side of things, right, we've been working really closely with our key partner, Rivos, in the server space, where we're helping. We have a dedicated team, which are both funded by Canonical and also Rivos, where we will build a optimized Ubuntu image where it can be maintained for 12 years, and then there's an option for Rivos to have some of their software packages rebuilt according to some of the tool chains that they have developed, and these are going to be like optimized Ubuntu packages that they can swap out from our generic Ubuntu build to use some of their accelerators in their system. So in the end, what's going to happen is it's going to be like super optimized Ubuntu image where there's these packages that's specifically developed for Rivos to be available on here. And this is something that we do in collaboration with them over here. And then through this collaboration, we're also working towards supporting RBA23 because most of the ecosystem is moving towards this. And then from 2510 onwards, which we're going to be releasing in October, we are going to be fully supporting RBA23 on this. And then that's going to be an interim release. And then by 2604, which is going to be a long-term release, that's when we're going to have like a 10 to 12 year support for RBA23 on this. And then whatever that is not RBA23 can remain on our LTS version 2404 that we are currently that we will be supporting until 2036. Yeah, so that's what we're doing here, and we're going to be making a release on our RBA23 strategy and how everything fits in the ecosystem very soon. So stay tuned. We'll be publishing that very soon. And that's it for my talk. It's quite fast, so I'll take us any questions that the audience may have.
Well, Otto's first. Fernando, do you have anything you'd like to say? Okay, I have a question. So, because you're partnering with Rivos and to make a big shift from RBA22 to RBA23, does it both move? I mean, did they? If it's confidential, then just say you cannot say it. So are they promising that they will shipping a lot of hardware that will be RBA23 compatible? Otherwise, that in the wild, in the open market, that there's 0 to none existing hardware that is RBA23 capable. And during the RISC digital meeting, Red Beard from Red Hat actually pointed out that they might not migrate to RBA23 because there's no real hardware for RBA23. So that's my question.
Yeah. So I think we get a lot of these questions, but I think from Canonical's perspective, right, we do want to push forward the technology, right? Like obviously now there's no hardware available yet, but we do see that there's going to be companies coming with the hardware. For example, K3 from SpaceMid is going to be the first one available, and it's going to be available by the end of the year, and we will be working with them to enable that. There's also
SpaceMid K3?
Yeah, SpaceMid K3 is going to be one. And then, although the Ultra RISC one is not going to be fully RBA23, yeah, so that one is something that they're working towards as well. And then with, we also have Alibaba, right, and Zhihe Computing, right, and they're going to be available sometime around early next year. So we see like a market moving that way, and we want to be able to support some of these people that are trying to meet some of the RBA standards that are being pushed forward by RISC-V International. But at the same time, we do understand that there are still going to be a lot of hardware vendors that are not yet following RBA23 yet. And we have a solution to that, right? Because on 2404, it's long-term support. It's supported until 2036. So we're not abandoning the older RBAs. It's just that we prefer to have them be maintained on in older version, and we can target newer versions with the newer releases.
From my understanding, it's a little bit like the. From my understanding, it's a little bit like the good old ARM HF and ARM EL. You know, back then the ARM HF had the VFP and those fancy ass neon and stuff like that. So many distros such as Debian, they have like 3 or 2 API variants. For the ARM HF, you can toggle it with the newer ARM v7, and for the older ones, ARM v5 or v6, you need to use ARM EL. And that's a big division that cannot be resolved now, even to nowadays. That for distros like Arch ARM, they need to divide the build procedures and stuff like that into 2 sets of the CIs and things like that. So I'm not sure whether Canonical is prepared for it, but if that's the case, then where will it do it? So I'm just curious about your point of view, and thank you for explaining it to me.
Yeah. I'm sure we'll have a more comprehensive explanation on that, I would say. But I think
just let time do its job.
Yeah, exactly. Any other questions from the audience?
I see we have many RISC-V vendors you supported in your slides, and one question I want to ask about, I see Alibaba, TheAD, or some Ventana, some other vendors. I believe they have their own customized instructions for performance enhancement or some other things. What is your strategy to support different CPU vendors to optimize for their Ubuntu build, or they still use the same Ubuntu build for every different CPU?
May I say a couple of words about it? Because actually we come to Gordon saying we're asking the same question, and we actually want to have the bootstrap flow for Ubuntu so we can recompile the whole world with our constant extension to get performance, but that idea seems to be shut down. So I have the same question from Brintan as well.
Yeah, we actually get a lot of questions, and that's what we're doing with Rivos right now, right? So at the generic Ubuntu, right, we would build for standard RVA 23, right? Anything that's listed as mandatory from RISC-V International, we build our archive based on those extensions. And then there's optional extensions from, say, Sci-Fi or from other people. Then this is where we have a strategic partnership. That what we do is we have a team where we would take these extensions, whatever you do on the GCCs or LLVMs, right? We would you tell us whichever packages you need to rebuild. We'll put them into a PPA,
Okay.
and then we maintain that PPA for you throughout the life of the LTS, for example, right? And then during runtime, we will detect your hardware, and then if it's like Sci-Fi hardware or ND's hardware, then it gets swapped out, right? Whatever packages that need to be swapped out, then that's what we do. And then it works pretty well for now, at least, is that there's some stuff that you don't want to probably be public right now. Like at least for Rivos, they don't want anything to be, some of their proprietary stuff to be public. So it gets locked up, and then we take care of it that way as well. It's easier for them to control some of the access.
Do we have any follow-up?
So even the tool chain, they have a specific tool chain for their own, then you would maintain it in your private repo.
Yeah, so they have their own specific patches from their tool chains, and then what happens is, like, you know, there's a list of packages that they need us to rebuild with their tool chains. So and then we just help them rebuild it, and then we maintain it on their private repo. Yeah.
So So my question is that because for all right, let me rephrase that. Is our BPA to be regarded as a sub-architecture, like because if we know for they have this kind of, just like I said, EHF, EL, so it's like a sub-variance of the ISA. I mean, in the build files, you can specify the architecture things, and our custom instructions or stuff like that. Are we going to be regarded as something like sub-architecture, or is it completely different ISA string and stuff like that? So maybe I can dig deep into it.
Yeah, I mean, it's a little bit too deep for me. Maybe I need to have an entry.
Okay.
But then again, like I think the whole concept around here is that generic Ubuntu. We don't want to be we don't want we don't want to be biased towards. We want to make sure that it's generic as possible. There will be situations where people that are, let's say, very low cost RISC-V vendor that does not have any optional extensions, that just want to use Ubuntu. Yeah, they can do that, right? We don't want them to conflict with anything. If we build something with the optional stuff in the generic Ubuntu, then it's not going to work for them, and that's not something that we want to get into, right? So I think that's the whole gist of the whole situation at the moment.
In a high conceptual level, I can understand that.
Yeah.
Any more questions? Okay, seems no. We actually have 3 minutes for the next talk, and let's give a big applause to the.
Good afternoon. It is a pleasure to be here at this conference, presenting to such a passionate open source community. My name is Kuan-Yu Chen, and I am currently a senior design engineer in the RISC-V team at Storrent. Today, I will be introducing the Ocelot project, an open source project that enables RISC-V vector extension support to the Boom core. The story behind Ocelot is deeply intertwined with my own journey. I worked on the second generation of the project during my internship. After completing my internship, I rejoined Storrent full-time, and I've been one of the main maintainers of the project, working alongside a team of incredible engineers. In this talk, I will not only dive into the technical challenges solutions involved in enabling vector extensions on the Boom core, but also share the insights I've gained about open source hardware development. By the end of this session, I hope to inspire more people from the open source hardware community to explore projects like Ocelot and push the boundaries of what open source collaboration can achieve. Let's get started. Before we dive into the Ocelot project, let's first answer a simple but important question. What is the Boom core? Boom stands for Berkely Out-of-Order Machine. It is an open source RISC-V processor core developed at UC Berkeley. The Boom core is an out-of-order superscalar CPU, which makes it powerful and suitable for our project. What sets Boom apart is its customizability. You can configure architectural parameters like the instruction issue width and memory interface width, making it suitable for a wide range of workloads, from research platforms to FPGA prototypes and even full ASIC tapeouts. On the right, you will see a block diagram of the Boom architecture. If you have experience with modern out-of-order processors, many of these components will look familiar. There is the front end with the fetch and decode units, a reorder buffer, issue queues, and of course, execution units for integer and floating point operations. The Boom core is integrated into Chipyard, an open source SoC development framework also developed at Berkeley. Chipyard provides a cohesive environment for design simulation, testing, and integration with other IP blocks. It is what makes experimenting with designs like Ocelot so much more accessible to researchers and engineers. I have included a link to the official BOOM documentation here on the slide. The maintainers have done a great job providing clear and thorough technical guides, which are invaluable during our work. Our project, Ocelot, builds on top of this ecosystem. Specifically, we aim to extend BOOM to support the RISC-V vector extension, or RISC-V, bringing powerful SIMD-style comparison to an out-of-order architecture. Now, let's talk about the why. Why do we need to support the RISC-V vector extension in the first place? The BOOM core, as we saw earlier, is already a capable scalar processor. It handles general-purpose computing tasks efficiently. But in today's workloads, scalar execution often isn't enough. This is where vector processing comes in. The RISC-V vector extension, or RISC-V, allows a single instruction to operate on multiple data elements in parallel. This is fundamentally different from scalar processing, where each instruction works on just one data element at a time. You can see a simplified example of this on the right side of the slide. Instead of writing a for loop that iterates through each array element one by one, say to compute C equals A plus B, a single vector add instruction can perform the same operation across an entire chunk of the array in parallel. That is a massive boost in throughput, especially when scaled to larger data sets. This is crucial for modern workloads such as AI, machine learning, scientific simulations, and multimedia applications, where data parallelism is key to high performance. By integrating vector support into BOOM, we are enabling it to tackle these data parallel workloads heads-on. We are essentially transforming BOOM from a general-purpose CPU into a much more versatile compute engine, capable of handling modern compute-intensive tasks with efficiency. And more importantly, we are doing this in a way that is open source and accessible. This makes it possible for researchers, educators, and hardware developers around the world to experiment with real-world vector workloads on a customizable out-of-order core. Most of the open-source RISC-V CPUs that support the vector extension today are in-order cores. These designs are typically simpler and easier to implement, which makes them a natural first step for exploring RISC-V. However, they also come with important limitations, particularly when you are dealing with complex workloads that have branching logic, memory latency, or variable length operations. On the right, we have shown a conceptual comparison between in-order and out-of-order processing. In an in-order core, instructions are fetched, decoded, and executed strictly in the order they appear. If one instruction stalls, say waiting for memory access, all following instructions are blocked, even if they are independent. Out-of-order execution, on the other hand, is smarter. It dynamically schedules instructions, reorders them, and tries to keep execution units busy as long as the dependencies allow. This becomes especially valuable when working with vector code. The BOOM core is also superscalar. It can issue multiple instructions per cycle and reschedule around stalls dynamically. This means better pipeline utilization, higher instructions throughput, and ultimately better performance, especially on real-world applications with irregularities. However, combining these powerful features with full vector support introduces significant technical complexity. From handling long latency operations to managing hazard detection and scoreboarding, there are many challenges under the hood. And that's exactly what makes the Ocelot project both ambitious and impactful. We are tackling one of the harder problems in open source hardware and making it available for the broader community. The Ocelot project has evolved significantly over time. What began as a tightly coupled prototype has grown into a much more modular and standards-aligned vector processing system. The first version, Ocelot 1, was the initial proof of concept. The goal was simple: get vector support working on BOOM. To do that, the team developed a custom vector processing unit, or VPU, and directly connected it to the BOOM core. This tightly coupled integration allowed the scalar core to issue vector instructions and offload them to the VPU for execution. While it worked, this design was very specific and rigid. It tightly bound the boom core to a specific VPU implementation. That meant it was hard to reuse or replace components. So, for the next iteration, we decided to rethink the architecture. That brings us to Ocelot 2, which is the generation I worked on during my internship. In Ocelot 2, we adopted the Open Vector Interface, OVI, as the communication layer between the scalar core and the VPU. The OVI is an open source interface standard originally developed by Semidynamics that defines a clean, decoupled protocol for how a processor core and the vector unit can talk to each other. This shift to OVI was a major architectural improvement. With OVI in place, both the boom core and the VPU became modular components. That means you can mix and match, plug in different VPUs or a scalar core, as long as they speak OVI. This opens up a lot of flexibility for research and development. You can, for example, compare different VPU designs or upgrade the scalar core without needing to rewrite the entire system. From a community perspective, it also promotes collaboration. Teams across different organizations can now build to the same interface and share components more easily. Beyond just adopting OVI, we've also introduced targeted optimizations, especially for vector memory instructions, and continue to improve Ocelot for more robust and efficient vector processing. Here we have the high-level architecture of Ocelot 2. On the left side, we have the boom scalar core. This is the out-of-order superscalar CPU that handles all general-purpose scalar instructions, branches, integer math, control flow, and so on. On the right, we have the vector processing unit, VPU. This is a dedicated unit that executes vector instructions. These two are connected through the Open Vector Interface, OVI. When the scalar core decodes a vector instruction, it passes it over to the VPU via OVI. The VPU handles the actual execution, and once the operation is done, the VPU updates the scalar core's reorder buffer, which ensures that instructions retire in program order and that exception handling remains consistent. This decoupled setup brings several advantages. For one, it separates concerns. The scalar core doesn't need to micromanage vector execution, and the VPU can evolve independently. It also simplifies debugging and testing, since you can simulate or even replace one side of the interface independently of the other. One thing to note is that you can see at the bottom left of the diagram, the scalar and vector operations share the same load store unit, or LSU. We added a vector load store unit, VOSU, that acts as a bridge between the VPU and the LSU. It translates vector memory requests into a format that the shared LSU can service. The VOSU handles address generation for various access patterns, and the LSU ensures that memory access from vector instructions respect the same ordering and protection rules as the scalar side. Next, we will look more closely at the VOSU itself and the specific challenges we had to solve to make it performant and correct. One of the biggest challenges in any vector processor is memory access. Even if you have a wide, high-performance vector execution unit, its throughput is often limited by how quickly you can feed it data. This is especially true for data parallel workloads, where large arrays of matrices need to be moved in and out of the processor constantly. In Ocelot 2, we focused heavily on optimizing vector load store handling. The vector load store unit, VOSU, is shown in the diagram on the right. The VPU issues a vector memory request and is broken down by the VOSU into scalar-like accesses, allowing them to integrate seamlessly with scalar requests through the original load store unit of the boom core. From the LSU's perspective, it is just seeing a stream of smaller memory requests, which means we can reuse the boom's mature out-of-order memory system. Inside the boom LSU, we added dedicated load and store queues for vector operations, while leaving the existing scalar queues intact. This separation prevents vector traffic from stalling scalar memory operations unnecessarily. At the same time, it minimizes how much we had to modify the proven LSU design, keeping the scalar course behavior stable and reliable. To further improve performance, we also introduced vector-specific optimizations. The first one is request packing. For smaller data types like 8-bit or 16-bit elements, the VOSU packs multiple elements into a single transaction. This ensures we fully utilize available bandwidth instead of issuing a flood of tiny, inefficient requests. The second one is mask skipping. Vector instructions often have mask bits, which specify which elements are active. The VOSU can skip masked off elements in bulk, reducing wasted cycles and memory traffic. Together, these optimizations reduce memory stalls and keep the VPU fed with data, which directly translates into higher vector throughput. These enhancements together greatly reduce memory bottlenecks and led directly to significant performance improvements. To wrap up the technical deep dive, let's take a look at some performance results. On the right, we have a table comparing the performance of Ocelot 2 versus Ocelot 1 across a few representative vector benchmarks, including convolution, inner product, and matrix multiplication. On average, Ocelot 2 achieves a 300% speedup over the earlier version. So where do these gains come from? First, from the optimized vector low-store path, which we just discussed. By efficiently translating vector memory operations and packing them where possible, we reduced memory stalls and kept the execution unit busy. Second, from the clean modular interface via OBI. This allowed the VPU to operate more independently, without needing tight coupling or ad hoc communication with the scalar core. It also simplified the control logic and improved scheduling flexibility. And finally, by keeping the boom course low-store unit largely intact, we benefited from a well-tested, high-performance memory backend, avoiding regressions or unnecessary redesigns. That wrapped up the technical details and results of the Ocelot 2 project. I collaborated with another intern on this project during a 3-month internship. Looking back, I truly believe that this project is an ideal fit for interns or newcomers to hardware design, and here's why. First, it is a standalone project. The vector processing unit and the OBI interface form a self-contained design space. This means you don't have to touch every part of the system to make meaningful progress. You can focus on a well-defined component, which is really valuable when you only have a few months. At the same time, Ocelot is built on top of Chipyard, the open source SoC development framework from Berkely. Chipyard brings with it a mature simulation and verification environment, including test harnesses, runtime tooling, and debug infrastructure. That means you don't have to spend half of your time building scaffolding just to get your design running. You can plug in your module and immediately start testing. This combination of independent ownership and strong infrastructure support is rare, and it's exactly what made it possible for us as interns to ramp up quickly, contribute meaningfully, and see the results of our work in action. Tenstoran is committed to supporting and contributing to the open source community. For example, our AI compilers are fully open source, and the Ocelot project is one of our open source hardware initiatives. Throughout my work on Ocelot, I've also been reminded of how much we ourselves benefit from the open source ecosystem. In particular, we have relied heavily on frameworks like Chipyard, which provides a scalable infrastructure for simulation, testing, and integration. We also utilize Whisper, which is Tenstoran's own open source instruction set simulator for RISC-V. These resources and tools not only accelerated our development, but also connected us to a wider community of contributors. Next, I would like to share some insights from these open source experiences. One of the most important factors that enable the success of the Ocelot project is the use of open standards. both RISC-V and the OVI are open specifications, freely available, fully documented, and developed in the open. Anyone can read them, implement them, give feedback, or contribute to improvements. And that openness fundamentally changes how we build. With open standards, we could engage directly with the communities and developers behind them. For example, during Ocelot 2's development, we encountered a few ambiguities in the OVI protocol. Instead of being blocked or guessing, we reached out directly to the OVI maintainers on GitHub. Open standards also promote collaboration and longevity. Because OVI is an open protocol, any team building a vector unit or scalar core can adopt it and know they'll be compatible with others. This makes the ecosystem stronger as a whole. Another major strength of open source development is the ecosystem it creates. In the case of Ocelot, we didn't start from a blank slate. Instead, we built on top of two powerful open source foundations, Chipyard and Boom. Because both of these projects are fully open source, we had direct access to everything, from the actual RTO source code to detailed documentation, simulation frameworks, test benches, and even historical discussions and commits that show how the designs evolved. Instead of guessing at architectural intent or spending months re-implementing basic infrastructure, we could study real design decisions, see how others had approached similar problems, and learn directly from their solutions and their mistakes. Open source ecosystems also encourage collaboration and reuse. As we worked on Ocelot, we were able to integrate with tools, modules, and utilities built by others in the RISC-V community. And in return, we contributed improvements back into the ecosystem. Instead of spending all our time reinventing the wheel, we can focus on improving Ocelot. Beyond the hardware itself, one of the often overlooked strengths of open source development is the availability of powerful, accessible tooling. The Ocelot project made full use of this, thanks in large part to the fact that Chipyard is designed to work seamlessly with a fully open source toolchain. One of the most central tools in our workflow is Whisper, an open source RISC-V instruction set simulator developed by Tenstorrent. Whisper lets us simulate programs quickly at the instruction level, which is incredibly helpful for debugging, validating instruction behavior, and checking edge cases before we even get to the RTO level. For RTO simulation and viewing waveforms, Verilator and GTK Wave are open source tools that are available. Together, these tools form the complete end-to-end open source toolchain, from high-level validation to low-level debugging. That makes our works transparent, reproducible, and shareable, all of which are core values in both engineering and open source culture. While open source development brings enormous benefits, including transparency, collaboration, and flexibility, it can also come with some very real practical challenges. One of the biggest hurdles we faced early on was simply getting the environment set up. As many of you may know, setting up Chipyard along with all its toolchains, simulators, and dependencies can be a complex and time-consuming process. It often requires a specific set of tools, versions, environment variables, and build steps. For someone new to hardware development or even just new to the project, this initial ramp-up can be daunting. During my internship, we ran into this firsthand. Every new contributor had to spend significant time configuring their machine before they could even begin meaningful development. To address this, we created a pre-built container image that packaged everything needed to work on Ocelot. By standardizing the setup in a single image, we were able to skip the installation pane and focus immediately on building, testing, and iterating. It also meant we could share a consistent environment across different machines and teams, reducing the "it works on my machine" problems. Most importantly, this container image is now publicly available, so that anyone who wants to explore or contribute to Ocelot can do so with just a few commands. No complex setup required. This approach lowers the barrier to entry, especially for students, interns, and new contributors. One of the more emerging benefits of open source development, and something I found particularly helpful during my internship, is how it enables the use of AI-driven tools in a safe and productive way. For example, Ocelot and Shipyard are written in Chisel, a powerful hardware description language based on Scala. Chisel offers a lot of expressive power and parameterization, but for someone new to it, like I was, it comes with a steep learning curve. Traditionally, learning a new hardware language meant reading documentation line by line or relying heavily on mentorship. But thanks to recent advances in AI coding assistance, I was able to accelerate the learning process significantly. These tools became a kind of on-demand tutor, helping me explore and navigate a large code base without having to constantly pause and ask for help. And more importantly, since the code was public, there were no confidentiality issues. To wrap things up, I want to take a moment to reflect on the journey of the Ocelot project and what it taught me about open source hardware development. From the very beginning, openness has been at the heart of this work. We built Ocelot on top of open standards like RISC-V and the Open Vector Interface, allowing us to collaborate and build confidently. We relied on a rich ecosystem of open source tools and designs, from Shipyard to Boom to Whisper, which accelerated our development and helped us avoid unnecessary reinvention. And we embraced modern workloads, including AI coding assistance, which helped us learn faster and work more effectively, without the risk or barriers of closed development. I would encourage anyone interested in computer architecture or hardware design to get involved in open source projects like Ocelot. It is a great way to learn, contribute, and connect with others driving innovation forward. If you have any questions about Ocelot, you can always reach me at the email address listed here. Thank you for listening and have a nice rest of your day. Thank you.
Okay, so that's all the talks we have today, and if you're basically I'll be wrapping up all the gears I bring up, and if you want to leave, just feel free to leave and go to the big stadium for the closing out for COSCUP. And again, thank you all.
Thank you.
By the way, so ExpressVPN is so what you're trying to do is to build a custom built machine to run your VPN stack. Is that what you're trying to do? Because I'm a little bit kind of
November 8th.